Hello and welcome to this design practice 2 module 22. I will be talking in this particular section about again actuators and sensor design, and we had already covered the microvalve portion, particularly the microvalve which is actuated with different non-conventional schemes like electrochemistry, for example, or thermonumeric or thermal, or even very advanced effects like electrowetting effect or thermocapillary effect, etc. I will be now in today's module talking mostly about micropumps and how actuation is done within those micropumps. It is very important for particularly people who are in this area of designing of MEMS systems or small systems to understand the modalities which are associated with device design of such devices at the microscopic length scale. And so therefore, intentionally this particular module has been introduced to give them the backup technical support which is needed for understanding the design at that particular small scale. So let us talk about micropumps. So obviously the first categorization which happens in micropumps is based on the principle by which energy is applied to the particular fluid. It can be categorized as either mechanical energy or non-mechanical energy, and based on whatever is the form of energy, you can have mechanical micropumps or mechanical pumps or non-mechanical pumps. So the mechanical pumps again are classified further based on the principles by which this mechanical energy would be applied. Under the system, the mechanical pumps are either dynamic or displacement type pumps. In dynamic pumps, we are talking about a rotary component mostly, and in displacement pumps, we are talking about a piston based linear movement of the actuation mechanism. The displacement pumps are one in which energy is periodically added, probably by application of force to one or more movable boundaries, any number of enclosed fluid volumes, and this results in a discrete increase in pressure, because of which fluid is forced to go out or any medium is forced to go out. Many examples of the displacement pumping domains could be, for example, check valve pumps, peristaltic pumps. I am going to talk about this in great detail to design them. The valveless rectification pumps, the rotary pumps, so on and so forth. So in the dynamic pumps, mechanical energy is continuously added to increase fluid velocities within the machine. The higher velocity at pump outlet increases the pressure, and this leads to the discharge, the forward discharge. Some examples could be, for example, centrifugal pump or ultrasonic pump, where energy is continuously being applied, okay, not in discrete form. So these are the basic classifications of pumps when we talk or start talking about micropumps, and then there are many non-conventional, non-mechanical processes which are related to again the fluid flow aspects, the fluid behavior aspects, for example, surface tension, again electrowetting, electroosmosis, osmosis, ferrofluidic, so on and so forth, where the nature of the particular fluid would be responsible, and its interaction with the surfaces of the devices would be responsible for the forward movement of the fluid. So in the non-mechanical pumps, we add velocity to the fluid by adding momentum to the fluid in some other term. Typically it is by converting another non-mechanical energy into kinetic energy. Okay, this non-mechanical may be electrostatic energy, or for example surface based, surface tension based energy, so on and so forth. So mechanical pumping, if we look at, is mostly used in the macro scale, because in micro scale flows or micro scale flow control, there is always a scale effect which comes, and inertial effects are not so prominent because of the miniaturized size of the fluid that we are handling. So therefore there is a second category of non-mechanical pumps which discovers and applies very highly to the micro scale. So again, if I looked at the characterization of the different principles or classification of the different principles of the non-mechanical pumps, generally they are classified either as fluid flow case or a solute flux case. For example, in the fluid flow case, there can be a pressure gradient created by surface tension. You already saw the electrowetting or thermocapillary effect. It is also otherwise known as the Marangoni effect, or by surface modification you could actually create a gradient surface energy surface through which increasing hydrophilicity may be, through which a water droplet can move uphill, or for example a water droplet can move between one place to another at the same potential level, but it happens because of the gradient surface that has been created with different surface tension, so on and so forth, surface energy, so on and so forth. So, in the fluid flow based pumps, the concentration gradient can be established through again osmosis processes, just as you saw the movement or pressure gradient being established through surface tension. If you have a membrane, a semi permeable membrane, and you have a differential concentration of a particular analyte on both sides, obviously there is going to be a solvent flux from the richer side to the leaner side, so that there is balancing of concentration on both sides. So, if there is such a gradient which exists and across a membrane, there is always almost the possibility of mass transfer to happen, so that the concentrations on both sides may become equal. Again, there can be diffusion driven. So, when we talk about solute flux, we can talk about diffusion driven flux, where the physical molecules would move diffusively from the higher concentration side to the lower concentration side in a fluid path, and it would again create equality of concentration on both sides. So, the driving factor here is the concentration and a concentration gradient. Again, there can be electrical principles applied, electrical potential applied to create the gradient. One of the very commonly available effects is called the electroosmosis effect, which is about creating of a double layer on a surface by virtue of change of the zeta potential of the surface as it comes in contact with the fluid. And because of the double layer, by applying a perpendicular field, you can migrate a particular fluid volume like a plug, okay, and so that becomes again electrically assisted or electrically driven or electrical potential driven flow phenomena where there is fluid flow. So, there is also electrohydrodynamic principle which relates to a dielectric fluid which is being pushed into one particular zone of a flow stream. There can be electrophoresis, where there are charged particles migrating within fluid flow, which are again driven through an external field, and then finally dielectrophoresis, which is because of the change in the electrical permeability of the medium with respect to let us say some particles or some two phase of a second phase, for example a gas within a liquid, because of which there can be migration towards the lower electric field zones from the high electric field zone. So, these are different electrically applied gradients where potential difference would be the cause of movement for in some cases solute flux to happen, or in some cases fluid flows to happen. Again, you can have, just as you had all these non-conventional concentration driven, electrical potential driven, you can also have a magnetic potential driven set of micropumps in these non-mechanical category, where we can talk about ferrofluidic pumps, for example. I will come to these while we do explanation for each of these categories, or magnetohydrodynamic flows, so on and so forth. So, having classified into various types, the more important question that is asked here is that what is the flow range of such pumps and what kind of volume flows can it support. So, typically the flow rates in micropumps are ranged between what is illustrated here. In the mechanical case, you can see peristaltic pumps or valveless rectification pumps or check valve pumps, which I will describe design wise in the subsequent slides, having a flow rate close to 1 to 10 milliliter per minute in this particular zone. And when we talk about these other so called non-mechanical forms of energy being applied, like electrokinetic pump or electrohydrodynamic pump or magnetohydrodynamic pump or ultrasonic pump, they fall in a much lower flow range category between 0.001 to 0.1 milliliter per minute. So, it is about again a tenth of the minimum flow rates that can be obtained through mechanical systems. But then what is the reason why such new pumping principles and such innovative actuation schemes are initiated? And one of the major reasons is that in microfluidic flows, particularly when we are talking about applying these to human diagnostics, clinical diagnostics, etc., the volume is very low, and you have to have a very controlled motion of a very small amount of fluid within chip size platforms, so that they can have everything including signal transduction, the recognition of the element, the signal readability aspects, the interpretation aspects in a very small area. So, therefore, energy needed for such movements of minuscule amount of flows may be minimalistic, and mechanical pumps may not satisfy that kind of a range of flow requirements. So, therefore, new pumping principles are quite essential, and you will learn some actuation schemes from looking at some of these principles. So, how do you justify what kind of parameters are needed for controlling flows of micropumps, defining flows within micropumps? The most important specification basis for micropumps, are the maximum flow rate, the maximum back pressure against which the pump has to deliver, and ultimately the pump power and the pump efficiency. So, these are, you can call, the 4 indicative parameters for categorizing or classifying a certain micropump in different ranges. And the maximum flow rate or pump capacity, that is Qmax, is the volume of liquid which comes out or is discharged by the pump per unit time at 0 back pressure. Okay, so, that is how you are defining. So, the maximum back pressure is the maximum pressure the pump can work against, and at this pressure the flow rate of the pump becomes 0. So, basically the pump is just able to sustain no backward movement at a certain maximum level of pressure, which is then the back pressure. So, let us now compute the pump head, how we can estimate some of the parameters which are needed for actuation design or actuator design. So, the pump head H kind of represents the net work done on a unit weight of liquid in passing from inlet or suction tube to the discharge tube. So, let us say if P were the outlet pressure, so this can be represented as P by rho plus U square by 2G plus Z, the potential energy at the outlet, minus a similar aspect at the inlet. So, if we assume that the gauge pressure is 0 and pump operates from atmospheric condition and delivers again into the atmospheric condition. So, the static head at the inlet and outlet can be 0. And H max then becomes equal to Z output minus Z input. So, based on the maximum flow rate Q dot max, the maximum back pressure P or the maximum pump head H max, the power of the pump can be calculated. It is basically the pressure discharge volume product divided by 2, it is assumed that the volume flow rate picks up from 0 and goes to q dash max, which is the maximum flow rate, and so therefore the average flow rate can be taken to be just half of q dash maximum. So the pumping efficiency now can be defined as the total power needed by the pump divided by the power needed to actuate the pump. Okay. So that is how you talk about what is the inlet energy given per unit time versus what is the pumping energy that is actually needed to maintain the discharge at a certain rate, okay, per unit time. Let's understand this through an example problem. That will be probably better, so that you can think of the the actuation scheme design. So let us say there is a thermonumeric check valve pump. Check valve pump really delivers on the basis of whether the valve is switched on or whether the valve is switched off. Maybe there is a gravity flow in the way of a valve, and if the valve seat is open, then flow continues. If it is closed, the flow the flow stops. So the thermonumeric check valve pump delivers a maximum flow rate of 34 microliters per minute and a maximum back pressure of 5 kilopascals. So we have to actuate the thermonumeric mechanism. We have already seen this while designing the static valve example in one of the lectures. So here we are actuating a heater with a certain resistance to go up to a certain temperature, so that it heats up a hermetically sealed cylinder with, let us say, an air confinement, and the air expands because of Charge's law and creates a membrane deflection. Okay. And so if you can do it multiple number of times by making, let us say, or feeding the electrical heater with a square wave signal, where there is a heater on, heater off mode, and there is some kind of a pulse width modulation scheme where you can control the duty cycle and the frequency at which the square signal is being generated. You can multiply close and open the valve in a manner so that you can have an average flow generate across the valve. Okay. So this is how check valve pumps are really operating. Okay. So it's you have to first understand the basic principle before again starting the design. Okay. So there is a valve. Again, I am just illustrating that there is a heater. The heater is fed with the signal off and on. So you switch off or switch on, and then change the switch off switch on times at a certain frequency, so that you can have delivery of the pump at a certain rate. So in this particular case, the heater resistance for the particular design of this particular pump is around 15 ohms, and as a designer of these kind of small systems, you must, when you are designing actuation at this particular scale, you must be very careful about the different parameters which are there to define the performance or operability of the architecture that you are designing for. So the pump works with the symmetric square signal. With the maximum voltage of 6 volts at 0.5 hertz frequency. That means it is operating exactly once in 2 seconds, this voltage signal, and we now want to determine the pump efficiency. So the modus operandi that would be there to calculate the efficiency is given in the equation right here. So we want to calculate what is the power that the pump delivers in terms of flow and what is the power that is needed for the actuation signal, and then just simply compare them. ratiometrically to see what is the efficiency. So, the power of the pump will be calculated a priori. This is the maximum power that the pump can develop, is obviously equal to the maximum back pressure against which the pump can flow times the average maximum flow that the pump has, that is Q rod by 2. In this particular case, the pump operates against a back pressure of 5 kPa, so 5 into 10 to the power of 3, and the total maximum flow rate that the pump can provide is 34 microliters per minute. So, let us compute that. So, 34 10 to the power of minus 6 liters, and this is per minute. So, we divide it by 60 to make it per second, times 2, obviously it is Q dot max by 2, and so this comes out to be equal to, so this makes it 1.42 10 to the power of minus minus 3 watts. If we consider only the active half of the drive signal, which is a square wave as I told you, the electrical power input that is needed to sustain such a signal across a resistance which is given, power input that is needed to sustain such a drive signal, okay, will actually be what is needed for the actuation of the pump. So, P actuator. So, this is exactly half V square by R, because I mean, when we are talking about 0.5 hertz, it means that the powering happens exactly once in 2 seconds, and so does the depowering. Okay. So, you have exactly 2 seconds of powering followed by that of depowering. So, when we talk about one such square signal which has been given, the total amount of power that is consumed here is 6 square by 30. So, that is 1.2 watts, and therefore, in this particular case, if such a signal given has produced this kind of a back pressure or pumping power, then the efficiency of the thermonumeric pump or actuator is actually equal to 1.42 10 to the power of minus 3 divided by 1.2, that is 1.18 10 to the power of minus 3, or even better minus 1 percentage. Okay. So, it is 0.118%. So, this is how the efficiency of a thermonumeric pump is. So, as you know that the efficiency figures in this particular case is quite unreasonably low, but again you have to understand that because there are scale effects at the scales that we are talking about, it is almost always important for more power to go in the system in order to actuate or create different effects. So, I think I have made sure that I gave you some of the non-conventional ways in which non-mechanical pumping is carried out. I am going to also talk about peristalsis in some level of detail in the next class, and then discuss some schematics or designs of what kind of actuation mechanisms can happen for again initiating microflows in different levels, followed by maybe some introductory research grade material presentation in the area of gas sensing design. So, till and until then, I would like to end this module. Thank you very much for being with me. Thank you.